Good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione, and I have the pleasure of introducing this afternoon's speaker. And I hope I get it right, Professor Sugnet Lubbe, who is one of our own here in Stellenbosch. After her PhD, Sugnet worked for 13 years in the corporate world, in industry. And after that, she decided to become an academic, first at UCT, where she was for a few years as associate professor before becoming a full professor of statistics in Stellenbosch in 2017. And at the moment, she directs the Center for Multidimensional Data Visualization, MUVISO, which we will hear about just now. Sugnet is also a member of many statistical associations and institutes that I will not read because you can all read. Yeah. And one reason why we were very keen to have her speak is because she developed an open source software package together with some of her PhD students and collaborators and postdocs. And yeah, and we would like to advertise. So, Sugnet, thank you very much for being with us today. And we are very keen to listen to your talk. Yeah. Thank you.
Thank you very much for the introduction. And as Professor Petruccione said, I will talk a little bit about the maths behind biplots, but the main idea is to just show you all the different places where biplots can be applied, where we've done it in the past. And currently, the MUVISO flagship project is called Applying biplotEZ. And we are trying to get collaborators from other fields to collaborate with them to apply biplots to their data. What we found is that whenever you get a practical problem with some data set, then there's some little problem and you have to extend the methodology a bit. So it's not just straightforward applying data in, biplots out, but it is a collaboration and a research projects that we're looking for. So I want to start with a simple scatter plot. And this is a data set from the paper and pulp industry, one of the places where we've applied our methodology. And we're looking at the characteristics of paper from different pine species. And we have two aspects of the paper that was measured, the burst index and the tearing index. And I've made a scatter plot, and we can see that there's a negative relationship between the two variables. The different colors is different species, and essentially what the company wanted to know is which species are optimal in terms of the different paper and pulp characteristics. So I can take this biplot, scatter plot, and I can modify it a little bit by just moving the axes to the middle, and I can rotate it, and it doesn't change anything with respect to what we are representing. We can still read off the value for, take this one, for any point. If I want to know the burst index value for this one, I project onto the axis and it's 7. And if I want to know the tearing index, it is little over 11, etc. So the real data set is multidimensional, and we actually have 8 numerical variables. So what we want to do is we want to represent the whole data set, and we don't want to make 8 plots because we want to visualize it with a multivariate view so that we can assess the intervariable relationships. And then instead of a scatter plot, very similar to this plot, I now have a similar one, except that I have 8 axes. And this is now a principal component analysis biplot of the data set. So how do I get this biplot? Principal components is the simplest form of a biplot, and I'll show you some others later on. But when we talk about principal component analysis, typically we start with our data matrix and we think about Hotelling's point of view, where we're looking for linear combinations of the variables to maximize the variance. And then we do that successively so that the kth linear combination maximize the variance subject to being uncorrelated with the previous ones. And if I take my centered data matrix and I compute my covariance matrix, then the principal components are given from the spectral decomposition as the linear combination. The kth principal component is x times the principal component loadings, which is the kth vector from the spectral decomposition. And of course, we are assuming my eigenvalues are ordered from large to small. So if I want the first R principal components, I will take the first R columns from my V matrix, and that provides me with my principal component scores. And if we look at the Y matrix, the covariance of the Y matrix, Y is X times V, and V is an orthogonal matrix, so that the covariance matrix is diagonal. So they are all uncorrelated, and the variances are ordered because the values in the eigenvalues in lambda is ordered. And then I can say that the first R principal components account for, and I take the sum of the first R eigenvalues over the sum of all the eigenvalues, and that gives me the proportion of the variance that I'm representing in my principal components. When we construct biplots, we are more interested in the principal component viewpoint of Pearson from 1901, where he looks at points in a high dimensional space and approximating them in a lower dimensional space, and he talks about a best fitting line or plane. For biplots, we're typically looking for a plane so that we can make a two-dimensional plot or sometimes a three-dimensional plot. And if I take my data matrix X, then essentially what I want to do is approximate it by matrix X hat of lower rank. And typically, as I said, we want R equal to 2 or 3 to make the biplot, although the mathematics work for any dimension. So if I look at the singular value decomposition of my matrix X, what I want to minimize is the Frobenius norm between the data and the lower rank matrix X hat. And based on the Eckert and Young theorem, that is given by essentially the first R columns of the U matrix, the first R singular values, and the first R columns of the V matrix, or first R rows of the V prime matrix. And then the two views of principal components is the same thing. That's why they're both views of principal components. So if I start with my singular value decomposition, then if X is UdV prime, then XV is equal to UD. And X prime X will be VD square V prime. So from the first point of view, we said that the covariance matrix is 1 over n minus 1 X prime X, which has a singular spectral decomposition. So we see that n minus 1s is the same as VD square V prime, or then n minus 1 V lambda V prime. So that the D and the lambda, the eigenvalues or squares of the singular values, the n minus 1 is just a nuisance factor. And when I look at the second view, my best approximation is UJDJV prime, where the J matrix just picks out the first R columns or rows as appropriate. And I can write it like this, UDJ times VJ. And then if I have my principal components, which is XVR, VR is just VJR, and XV is UD. So I can say Y is that. So the Y is that part of the X hat matrix. And there I have it, the UDJR, that's the Y. And then I have the VR there. So essentially, the only difference is that this is the principal components in terms of the basis of the principal directions. And this is the principal components in terms of the original Cartesian basis. And what we want to do is we want to represent our data X in 2 dimensions. So we want to have the X hat, which is the best approximation of the X that we have up there. So when we construct a biplot, as the name suggests, the prefix bi, we want to represent 2 things. We want to represent the samples and we want to represent the variables. So we represent the samples with the UDJR and the variables by the V times JR. And then originally the biplot was introduced by Gabriel in 1971, and Gabriel represented the samples as points and the variables as vectors originating from the origin. So a sample, the ith sample will be a point in my 2D space. There's my origin. And my jth variable will be a vector from the origin to there. But then Gower and Hand published a book in 1996, which was just before my PhD, and that sort of was where my research career started, where they then said, but we can view biplots as the multivariate analog of scatterplots, and we can construct scatterplot axes for the biplots. And it's based on some simple algebra. My best approximation X hat is the UDJR I'm writing as G, and the VJR I'm writing as H. So the ijth element is given by the inner product of the ith row of G and the jth row of H, or jth column of H prime. And the inner product can be written as this identity. And then I just reshuffle it. I say it's the length of the H times the length of the G times the cosine. And the length of the G times the cosine, that is AB times the cosine, is equal to AC. And AC is along the H vector. So it's a scalar multiple of the H vector. And now I can solve for C from X hat ij equal to that. So C is equal to this. So if I want to read off the value X hat ij, I put a marker at that point, which will be C times this vector H. And any value on this line, I project orthogonally onto the marker, and that's the value that I read off, which is what we see over here. So I have different values, and I project them onto the axis, and I can read off the values. But when we construct a scatter plot, we don't put the actual observed values on the axes. We put nice scale markers. So for instance, if your data is somewhere between 1 and 10, then you put scale markers 1, 2, 3, 4, or maybe 2, 4, 6, 8, etc. So we select nice scale markers mu, and then from this formula, the calibration factor, which is C mu times that H, is given by that value. And then along the axis, I fit the different markers along the axis to at these coordinates. The only difference between here and there is that I have to remember I'm working with my centered data matrix. But when you plot the data, you want to see your original units of measurement. So we just have to take care of the centering as well. Sometimes we don't only center, we also scale. We divide by the standard deviation if my variables are in very different units. And then, of course, I have to take that into account there as well. So what I've been showing you up to now is part of the truth, and that is the middle column, where I say we represent our samples with UDJR and our variables with VJR. In general, if we have our singular value decomposition, we can represent the samples as UD alpha, D to the alpha, and the variables is V D to the 1 minus alpha, where alpha is any value between 0 and 1. But what Gabriel showed in his original paper is if we have this selection, then we get that the XX prime, the matrix, the best approximation, the X hat prime is equal to the inner product of the G's, which means that the distances between the sample points, which I represent by the G's in the biplot, is equal to the distances of the X hats. And the X hat is the best approximation of the X. So I am optimally approximating the distances between the samples. If I rather say, let alpha be equal to 0, then I have G is UJR and H is VDJR. Then what I get is that the inner product of the X hat prime X hat is equal to the HH prime. And with some mathematics, I can show that that means that the cosine between the vectors is equal to the correlation of the X hat variables. So then I am optimally approximating the correlations in the original X matrix, because the cosines of the angles is the correlations of the X hats, and the X hats is the best approximation of the X. So I'm optimally approximating this. I can either do this or that. This one is optimal for the distances between the samples. This one is optimal for the angles between the variables. Or I can do anything in between, but then neither of the two is optimal, and they are both suboptimal depending on the value of alpha that I choose. So just to show you, here I have the biplot that I showed you earlier, which is the middle column, the same as the principal components. We have the linear combinations. And here we have the one where the angles between the axes optimally approximates the correlations. And we can see that it's very similar. There's some small differences. For instance, this angle here is smaller than over there. And you can see these two samples here are further apart than the two samples there. But all in all, it's exploratory analysis, and it tells you the same story. What you see over here is the R calls from the biplotEZ package to construct the two different biplots. So we don't have time to do a whole talk about how we construct the different biplots, but from time to time I will just show the calls on the screen. And the package that we developed is called biplotEZ, for easy to use biplots. And it is a set of functions that was developed by many researchers and postgraduate students over a long period of time, about 25 years. And we originally started and we just had a PCA biplot. Then we added the two different ways of the optimal samples or the optimal correlations. Then we added something else, then we added something else. So over a period of time, it became very clumsy, etc. So then when Movisu was formed, our first project was to take all the code and write a nice, easy to use package and make it available on CRAN. Because up to then we had R code and we even had it in package format, but it was never available on CRAN. So now we have this and we are still working on it. We're adding different types of biplots and some functionalities about changing the labels, etc. But the basic biplots is available, and we believe, well, at least compared to everything before, it is easy to use, and it's a unified syntax throughout the different types of biplots. So the other aspect regarding the principal component biplots is we are approximating my p-dimensional data with a rank 2 matrix, and how good is the approximation. And there we have a number of metrics for measuring the goodness of fit. And it's all based on this identity, which says that my X is the fitted plus the residual part. And then we can show that we can write it in this form. And because of certain orthogonality conditions that hold, that means that xx prime is equal to this, which is the x hat prime plus then the residual part. And the x prime x is equal to the to this expression here with its accompanying residual part. And we use this to then define a number of metrics. First of all, is we already said that the quality of the approximation is the sum of the eigenvalues over the sum of all the eigenvalues, and the singular values is the squared singular values is the eigenvalues. But also with this decomposition, we can show that it is the fitted part and then the residual part. And then we, in addition, we define the predictivity for the axes and the predictivity for the samples. And that is for each variable individually, how well the variable is represented. Sorry, there. And then for each sample individually, how well the sample is represented. And if a variable is represented very well, it means when you project onto the axis and you read off the values, it will be very close to the actual original values. If the variable is poorly represented, then you can expect an approximation that is not as accurate, because we are approximating high dimensions in 2 dimensions, and we do lose something in the process. So just to show you for the pine species data, it doesn't matter which decomposition we use, because it's the same X matrix, the same U, the same V, the same D. So in this case, the total yield variable is very well represented, and the alkali variable is not well represented at all. And in terms of the sample predictivity, I didn't label the samples here, but somewhere there's a sample number 2 that is very well represented, and a sample 24 that is very poorly represented. And you can also, with the biplotEZ package, you can have shading of the axis so that the better represented is darker shaded, or the size of the sample, so that a sample that is very poorly represented is just a dot on the plot, while one that is well represented is a box, as you see over there, or whatever plotting character you use. So then you know, if you look at something, that there is a which ones are well represented and which ones not. So I just want to show some more examples where we've applied this methodology. And this one is the so-called common padloper tortoise. And they don't have an English name for this tortoise. It's a tortoise that we find in South Africa, specifically in the Western Cape. And we have 106 samples on 17 variables. We actually had 109 samples, but 3 of them were contains missing values. So for the purposes of this plot, I simply removed the 3 samples. And then because we work with this, when the tortoises grow, a small tortoise has a small length, a small width, a small height. A large tortoise, everything is large. So growth is exponentially, and for that reason, we often use the log of the values when we look at the data. And we find for the first principal component, because all the variables are highly correlated, because the small tortoise has small width, length, height, the large tortoise has large values. All the, sorry, wrong button. All the variables are positively correlated, and then all the principal component loadings have the same sign. And they're unique up to multiplication by -1. So if they're all minuses, I can simply multiply them with -1. And then it means that my first principal component is essentially a weighted mean of the different measurements of the tortoise. And we can view that sort of as a size component. So a small value on the first principal component, given that I've now made them all positive, means that it's a small tortoise, and a large value is a large tortoise. So what we wanted to look at here was specifically the shape of the tortoises and not the size. And for that reason, we can then use principal component analysis biplots, but we plot the second and third principal components rather than the first and the second. And this is what it looks like. So we have different regions, and you see that, for instance, the Fynbos Southern Cape, you have values here, you have values there, you have values there. Same with Eastern Cape, there's red all over. But the one that seems to be different is the Great Karoo, which is towards this side. And what we see is that these tortoises have lower values for carapace width and shell height, and also for carapace length. So relative to the other tortoises, they have a slightly different shape. And this data set was given to us by Nature Conservation, and it was a pilot study to show that they think there is a subspecies forming, and they want to apply for money to investigate whether the Great Karoo tortoises, because they're on the other side of the mountain, so they don't mix with the other tortoises, whether there's really a subspecies forming. And with a simple exploratory analysis, you can see that there is evidence that's worthwhile to investigate the possibility further. And then another example that I want to show you is a slight adjustment to the principal component biplots, and that's when we have observations made across time. And often it's financial time series, and in the paper I'm busy submitting for publication, I use a data set in R that is available in base R with daily closing prices of major European stock indices. But then I also have an ecological data set where they are measuring different water parameters in the Beaufort Sea. You can see it's a large data set, 41,000 time points. And what we want is that principal components do not take into account the ordering of the data at all. So if you make a PCA biplot and you connect the points in order, it often just looks like spaghetti because it goes this way, that way, wherever. But what I'm suggesting is an iterative algorithm where we start with the ordinary PCA and then we use isotonic regression to force them into order, predict it to the high dimensional space, and make a PCA biplot of that and iterate until all the observations are nicely ordered. And then we get something that looks like this. So here's the financial time series data, and I just use color to show the progression of time. And this is the Beaufort Sea data. So one can see, for instance, between points A and B, there was a big change in these variables, while there was a smaller change in these variables. And then between C and D, the change was mostly in terms of pressure, whatever that might be, etc. So this is just another application of principal component biplots. So now we've looked at principal components a lot. Looking at big data, the problem with big data sets is that if you plot too many samples, you end up with just one big blob of ink because you overplot a lot of the samples. So some suggestions that we've made, we don't have the perfect answer yet, is for samples, is if you have groups in your data, then instead of plotting each individual observation, just show where the group of observations is rather than the individual observations. And then in terms of the variables, to selectively only show a group of variables that's of interest. So we look at one group and then you can make another plot of a different group of variables. Or then to use the access predictivity and only plot those variables that are well represented. The ones that poorly represented is useless in any case. So don't plot lots of stuff on the plot that is not very useful. So in terms of, for the samples, right slide. We make use of what is called alpha bags. And the alpha bags is based on the idea of half space location depth, which was defined in 1975. And essentially what it's about is if you take this point and you draw a line through your data, then you count how many samples on this side, how many samples on that side. And you rotate this line through 360 degrees and you count every time. So it's quite a computationally intensive way of computing the depth. But then, of course, if there's more samples on the side, then it is then it's a deeper point. And if it sits on the edge, then you're going to have 0 samples on that side and lots of samples on this side. It's not only for the samples, you can also compute the location depth of another point that is within the data set. So based on the location depth, Rousseau and Rutz and Rousseau defined a depth region, which then contains all the observations that is deeper than a specific value. And based on that, we then define the alpha bag as the convex polygon that contains alpha times n of the observations, where n is the total number of observations. So we typically like to plot some, say, 95% alpha bags or 90% alpha bags. So another example where we use the biplots is in sports science, where someone had these questionnaires. They introduced a rugby safety program called BoxSmart. And I think they introduced it in 2009 or something. So they started collecting data from 2008. And what they wanted to see is whether there's an improvement in the scores of how often people do the right things. So the right thing is to use a mouth guard. So if you use a mouth guard, you get a high score. If you don't use it, it's a low score. But it is a questionnaire asking players whether they do these things. And with all the data points, you can't really see whether there's a difference between the different years. But if I then construct 95% alpha bags, we can see that there were always people that did the right thing. But the ones that did not, as time goes on, it seems that there's more and more people that start to do the right thing. So it looks like the program did have an effect on what players do or not. And then in terms of the variables, this is also a questionnaire. There were 90 questions, which personally I think it's too many. If you ask someone, give him a questionnaire with 90 questions, you get fatigue and you don't get good quality data. But the data was already collected when we got involved. And they asked people, why do they buy from mail order catalogs? So that was before the time of Take a Lot, where you buy online, you buy it via the mail. And they grouped their questions into reasons, risks, and risk relievers. And here's the biplot of all the data. But then if I plot only, if I plot only the risks, then I've lost the reasons now. Okay, if I plot the reasons, you will see the numbers here, 21, 10, 33. They are all in this group over here. But then, and I can't remember what the different, I think the different colors were age groups of people. So you can see whether people perceive the reasons differently. But then if you plot the risks, you see that there's a lot of them that are all in this direction, except this one. And then if you plot the risk relievers, you see that one will fit in nicely here. So maybe it was the way they phrased the question that people perceived it differently. They perceived it as a risk reliever rather than a risk. The two things are related. So that is the use of biplots. Is it tells you what's going on in your data. It's all exploratory, but it can be very useful to understand what is going on in your data. So up to now, all the biplots have been principal component biplots, and we use numerical data. We can also incorporate categorical variables, and there's basically two ways in which that is done. The one is with so-called generalized biplots, where if you go into the theory with principal components, you can show that principal component analysis is basically what's called a classical scaling of Euclidean distances. And if you then replace your distance metric with a metric that is appropriate for mixed variables, then you simply apply the classical scaling, also known as principal coordinate analysis, to this distance metric, and you get a biplot. Well, you get a plot of the samples. That's not a biplot yet. So then you have to embed the reference system in the Euclidean space. That's another about 5 pages of algebra. And you then represent your variables in your biplot by projecting onto the two-dimensional display after the embedding. If your distances is Euclidean, you get your linear axis from principal components. But if you use a different distance metric, you can have non-linear axes. And then, of course, categorical variables, you get, if you have a variable with 3 different levels, then you will get 3 different points, which we then call category level points. And instead of reading off by projecting on an axis, everything that is closer to this category level point than that category level point is then predicted as being in this category rather than that category. So that's the one way. The other way is with categorical principal component analysis. And what we do there is we convert the category levels to numerical scores. Now, people often do that by saying, if I have 5 levels for my questions, completely disagree, disagree, neutral, agree, completely agree, they make it 1, 2, 3, 4, 5. That is not what we do here. We allow the data to suggest optimal scores. And what we want is that the U vectors contains the scores. The G's are just indicators so that G times U gives you the scores for the observed values. And then this H matrix is now my continuous, my numerical data, plus then the scores for the categorical data. And then we find the scores such that if I do PCA on the H, then I'm minimizing this criterion. And that means I need to know the scores to find the Z, and I need the Z to get the scores. So it is an alternating least squares algorithm. And what is then important is the solutions is not nested. So if you do principal component analysis, if you get 1 principal component, if you get 2, the first principal component is the 1, and you get an additional 1. If you do 3, it's the first 2 plus another 1. Here, if you do the solution for 1 dimension, you get a component. If you do it for 2 dimensions, neither of those 2 is going to be the first one, etc. What is nice about this method is it allows us to discriminate between nominal and ordinal categories, in the sense that when we update the scores in this alternating algorithm, if it's an ordinal variable, we can restrict the scores to be ordered so that you get ordered scores for your ordered categories, and for nominal categories, the scores will tell you what ordering comes out of the data. On the other hand, it's a linear method. So once you have scores, then everything is linear. While in this case, it is not. So I only have a categorical PCA biplot to show you. It's a very old data set, so it's not the current situation. But at some point, the university was worried about a remuneration payment gap between male and female staff. And we have here 4 numeric variables: the remuneration, the number of research outputs, the age, and the year since you obtained your highest qualification. And then we have academic rank, which is an ordered variable. So for the numeric variables, we have the axes as we've seen before. But then for the academic rank, you can see that this is rank 1, is junior lecturer, there's lecturer, senior lecturer, associate professor, professor. So you can see that instead of having a value, if you project onto the axis anywhere from here to there, it predicts rank 2. And then for the nominal variables, we also get linear axes. That's the difference with the generalized biplot. But there's no specific ordering for the faculties. And then we also have the gender in there as a variable. And then we also color-coded the samples according to gender. So we can see the difference. That side is if you project, it's female, but there's also male observations there. And that's the approximation. I'm taking 8 dimensions, approximating in 2 dimensions. So it's not going to be perfect, but you can see the differences there. So then a different type of data is compositional data. And compositional data is different from ordinary data. So compositional data, often it is percentages or proportions. So it's data that add up to a constant value, to 100% or proportions that add up to 1. It doesn't have to be. Here is another data set, and it's any data that has to be interpreted relatively. So this is, according to ChatGPT, this public spend by the United States on certain categories and South Africa. Clearly, the USA's economy is much bigger than the South African economy. So it's not the absolute values that's important. What's more important is the USA spend a lot more on defense than on public service. South Africa spend less on defense than on public. So it's relative to the other one. And for that reason, we interpret it in terms of ratios, and the standard multivariate data analysis methods do not apply. So we have to transform our data from the d-dimensional simplex, where the data is restricted to add up to some constant, to a Euclidean space, typically with log ratio transformations. And then we have the Aitchison geometry. So we cannot simply take the data and make a PCA biplot of the data. It's not going to give us any relative information. It's just going to tell us the US economy is much bigger than South Africa. So I don't have an economic example. The example that I do have is a genomics example. And the gene expression data is people analyze it, the absolute values. It's counts of taxonomic sequences. But if you look at how the measurements are made, technology, everything, what is important is the relative abundances of taxa. So in this is a longitudinal study of babies, and the different shades of blue is as we go along time. And then we have controls, and then we have babies that got pneumonia. And you can see there's a blob of pneumonia and there's another one. If I now add the different taxa, then you can see what is associated with these ones and which taxa is not. So that's just another example where we use the biplots. And then I want to talk a little bit about classification. And in classification, in addition to our X matrix, we have another vector of group membership. And we typically use an indicator matrix for indicating the group membership. We can compute a matrix of class means. And then there's a number of linear methods, which is all related. Canonical variate analysis, it's typically not that well known, but that is sort of the umbrella term. Linear discriminant analysis is a linear method. So you're looking for linear combinations of the data that will optimally separate the groups. Multivariate analysis of variance, where you want to test whether different groups differ statistically significantly. And all of this is basically the same set of theory, which relies on this decomposition of the total sum of squares into a between group sum of squares and a within group sum of squares. So what we want to do is we want to maximize the between class variance relative to within class variance. And with principal components, we typically place the restriction that the sum of the squared loadings equal to 1. In this case, we put the restriction that the loadings is the M vector, M prime WM is equal to 1. So we want to maximize this. We can take derivative, set equal to 0, and we get P solutions, P minus 1, obviously suboptimal, which is the solution to these eigenequations. And this one, you can say M is the eigenvectors of W inverse B, but we prefer to work with this one where we have a symmetric positive definite matrix with eigenvalues that are all real and positive. It just makes life easier for us. And then once we find the M vector, we can transform the class means to the canonical space. And essentially, that's what we want to do. We want to optimize the differences between the means. But when we make the plot, we don't just want to see class means. We want to see the data. We want to see whether the groups are overlapping or separate or whatever. So we also transform the original observations to the canonical space. And then we get something like this. So this is a mining example, a copper mine, where they make a copper froth. And the variables here, x1 to x8, is based on a visual analysis. They have a camera as the froth goes past. And then after taking the images, they translated that into 8 variables. One class is the optimal froth and the others are not optimal. And we see that in the first 2 dimensions, we get a good separation between this one and these. But the red and the green overlaps and the blue and the purple overlaps. So if we add another dimension, so here I have dimensions 1 and 2, and there I have 2 and 3. Then if you now imagine that this is a piece of paper and you are folding that part up towards you, then you have dimension 1, dimension 2, and dimension 3 is coming out of the screen towards you. Then these groups, red and green, they might look like they're overlapping with those, but they're already separate in these 2 dimensions. But here, the red one will then be down on the screen and the green one is up closer towards you. So in the 3 dimensions, you get a separation. And if you do the full analysis, you will find that you need a 4th dimension to also separate these 2. But you can separate all 5 of the groups. One specific application that's very important, and we often see it, is the 2-class classification. And with 2-class classification, there is this little problem that the canonical space depends, the dimension of the canonical space depends on the rank of the between class matrix. And if you have 2 classes, the rank of this matrix is 1. And what that means is when you make your transformation of your means to the canonical means, you get just 1 dimension and the rest is all zeros. In your eigenequation, the lambda has 1 non-zero value and the others are all 0. So there's no ordering in these values. And the columns that correspond to these values is one of infinitely many bases for that space. So how do we define a 2-dimensional plot that is unique? And for that, what we did is we said that when we transform it, then we can, just like with principal components, we can predict the original values from the canonical space. And because we only need 1 dimension for the means, if I predict the means, then I get exactly my original values. There's no approximation there. But that is not true for the samples. So the total squared reconstruction error for samples is not 0. So if we want to minimize that error, in other words, predict the samples or represent the samples so that they optimally represented, then we start with our original decomposition, and M1 is now the ones that, if it's a 2-class problem, M1 will be a vector that agree with the non-zero eigenvalues, and M2 agrees with the 0 eigenvalues. And then we need to compute the inverse of the M matrix, and we're specifically interested in that M2 matrix there. And this is larger than 0, so we look for a solution that will make this as small as possible. And if you read the paper and you go through all that algebra, then you find that if you take that M2 part and you take M2 times M2 prime, you take the singular value decomposition and you multiply the M2 with that V matrix, then you have, this will be then a column vector if I have two groups, and then the first column of this will then give you the best, the minimum of this error value, and the first three columns will then give you the best three-dimensional solution, etc. So here I then have a two-class problem, which comes from the wine industry. And when the grapes come into the cellar, they need to know whether there's rot in the grapes or not, because it influences the quality of the wine. It influences what you have to do to make good quality wine, and it determines what you're going to pay the farmer for the grapes. So you can take a sample, go to the lab, come back 2 hours later with observation. But what they're trying to do is to use infrared spectra to get an immediate reading. And then we want to say whether, based on the spectra, whether there's rot, which is the red, or there's no rot. And we had 100 different intensities at different wave numbers. We first did a variable selection and selected the best set of wave numbers, which happened to be 39. So you can see there's still a whole lot of them. But then this is now a two-group canonical variate analysis biplot. So this is the class mean of the non-rot variables, and you can go and read off on the axes what is the associated intensities, and different intensities is associated for different wave numbers is associated with different chemical components. So which chemical components are present in the rot and not the rot. And then this is the same data set where I just wanted to do something that's nonlinear. And I tried a SVM and it simply predicts everything is rot. So then I decided I'm actually waiting. This was the pilot study, and I'm going to get the data within a week or so, more data, so that this is only one region, and we want different spatial spread for proper data. So I didn't want to spend time on modeling data that I'm not going to use, so I just fitted a random forest. And what we see here is the orange areas is where we predict rot. The green is where we do not predict rot. And then we also define a region over there. You can see there's a lot of overlap where you can obviously, if the posterior probability for rot is larger than 0.5, you can say it's rot. But we rather say there's a gray area in between where you're not certain whether it's rot or not rot. And then there's, of course, different parameters that you can set. So how certain are you that it is rot or not? Then a little bit more on big data. I showed you the alpha bags and showing just some of the biplot axes at a time. But this is future work, is to introduce biplots for symbolic data analysis. And what is symbolic data analysis? Here I've used the standard data set from R, the diamonds data and the ggplot2 data set, 54,000 observations. And what I did was for each cut, color, and clarity combination, I summarized the data, in this case in an interval. So here, for a specific cut, color, clarity combination, all the carat values were between 0.9 and 3.4, etc. This is interval data, which is easy to show in a slide, which is the more interesting data, which is not that easy to show, is where for each of these combinations, instead of just having an interval, you have a histogram. So you get the spread of the observations in the interval. And then we want to construct biplots for this type of data. So if you have millions of records, you can summarize it, and then you get a biplot of each of these 276 rather than 54,000 observations. And then I want to end off with my two favorite applications. This one, we looked at different artifacts from the Middle Stone Age, and the red group is the oldest one. And as you can imagine, over time, things change slowly. So there's quite a lot of overlap, but you can see that in the older Middle Stone Age artifacts, you tended to have lower values for blade thickness and what is this word? Blade thickness and platform thickness. And then it started changing to the blue, and then from the blue, they sort of migrating in this direction. So you can see the overlap. You can also see where it differs and on which variables. And then this one is 3 types of Ukatia wood. This is, this one is stinkwood. This one is imbuya. This is another one, same species, but not used for furniture. And we had to classify a controversial chair, because if it's stinkwood, it's much more valuable than imbuya. So the measurements were made under a microscope, and then we simply add the sample to the plot, and we classified it as imbuya chair, which was unfortunate for the seller, but a useful application of our methodology. Thank you very much.
Very much for the very informative talk. Do we have questions for our speaker? Any questions? We have questions from our online audience. Not for the moment. You didn't show us how the software package works.
Yeah, well, we're actually planning to have another session. We want to talk to you about it through NITheCS.
Okay,
more like a day session where we then present the package and
nice.
hands-on how to analyze the data, how to make the different plots, etc.
Yeah. Very useful.
So in an hour or 40 minutes, I can only show you some code here and there. Yeah.
Thank you. There is a question at the back. Thank you very much. The microphone is on the way.
Thank you for that talk. I think it's nice to see so much of like data being represented. I wanted to know, maybe of late you could tell us like what is the most complicated system of things that you probably had to, represent in graphical form. I was especially intrigued by the, where you showed the distribution of the different ranks in lectures, senior lectures, and have you done a lot of those analysis? Because I think that could be quite useful in terms of, seeing like universities' progresses, comparing them, and so on and so forth.
Yes, for that specific one, we haven't. And that, as I said, that's a very old data set. And we have mentioned it, we must get an honest project, but it's so much effort to first get the data from the university, and it has to be anonymized, etc., that we'd rather do another honest project. But we had another one that was household survey data, where there was a follow-on, I think 8 years later or so, and then you can see how it moved. And something that I didn't have time to talk about is procrustes analysis, where you have 2 plots and you make the one fit optimally to the other one, so that it's easier to compare and to see how they differ.
Any other question? Here, please. Microphone was on the way. Deepika, can you please pass the microphone? Thank you.
Is it on?
Yes.
Yes. Okay, thanks for the talk. Just coming back to that plot that was mentioned concerning the publication output. I don't quite remember all the classifications in there, but could you also use something like the number of co-authors in such a?
Yes, definitely. I think this was, like I said, very long time ago when there weren't any H indices and all these metrics that we have nowadays. But would definitely be, you can also, sometimes the way they count it is they just count the units. So if you're one of two authors, you only get half a unit, whatever. But depending on how you collect the data, you can add whatever is appropriate.
Thanks.
We have questions from the online participants. Yes, just a second.
Hi. Okay, so we have two questions, Sugnet, please. Is the package based on Python and can we find it on GitHub? And there's another question, is it based in R and can you find it in CRAN and GitHub?
Yes, so yeah, the two questions are related. It is in it's in R. You can find it on CRAN. It's called biplotEZ. This is the page from R, from CRAN, and we are looking into Python. But on the one hand, we don't want to write it in both, because then every time you make an enhancement, then you have to do it twice, and then it gets out of sync and whatever. On the other hand, you can run R code from Python or Python code from R, but to optimally do that, so that is also not that easy. So we're looking at it, but at the moment it's not available in Python. But yeah, we are looking at it, and it is available in R on CRAN.
Okay, if there are no further questions, then Sugnet, thank you very much for the nice talk, and
Thank
we are
you.
looking forward to part 2, the practical
That's good.
session. And I think let me try not to forget, but I forget every week. It's a little gesture of appreciation, the Wizarco magazine that NITheCS
Thank you.
publishes. So
Thank you
that
very
you
much.
have time during your sabbatical to read it.
I hope so, yeah. There you go. Thank you.